Okay, hello everyone. In this video, which is the statistics series finale, we are going to be looking at the applications of and using confidence intervals that are not 0.95 confidence intervals. And I just want to point out the binomial distribution series I'm doing will be starting on the 25th of May, this weekend, the 25th of the 5th, 2013. So feel free to check that out. It'll be running for around about 3 weeks. So it should be quite interesting. It's a shorter module than the statistics module. However, we're still covering some cool stuff and it should be great fun. So, applications of and using confidence intervals that are not 0.95. Well, I do want to start the video by giving an example that looks at a 95% confidence interval, but it looks at something we haven't looked at over the last few videos, and that's actually making a claim that the likelihood of some value being the mean will be less than a certain percentage. And again, well, it's always good to make those sort of claims. So say that we are 10% sure that the population mean will definitely be, or we're 10% sure that the population mean is below 300, which for example would mean it's very unlikely that the population mean would be under 300. Well, I would say it's very improbable rather than very unlikely, but as you can see, we'll actually figure out a way of how we can check those proportions based on the confidence interval that we produce for a sample. So it should be a good video, and hopefully you'll be able to get some value out of it. So I've plugged my new series. I've talked briefly about what we're going to be doing for the first half of the video, so I think it's about time we get into it. And the first question talks about a restaurant food chain and a seafood wholesaler who is going to be inspecting a catch of 50,000 prawns. So 50,000 prawns is what the wholesaler offers. She has instructions to buy the catch only if the prawns are heavy enough. The buyer selects a sample of 60 prawns. N equals 60 prawns, and finds that their mean weight is 57.2 grams RB per prawn. It is known that the population standard deviation is 4.2 grams. So now, the first thing it's going to ask us is to actually calculate a 95% confidence interval for this mean mu here. So we've got our sample standard deviation, and we know for a 95% confidence interval, 0.95 confidence interval, it's simply x bar take 1.96 sigma over root n less than or equal to mu less than or equal to x bar plus 1.96 sigma over root n. Again, if you're not sure about that, maybe it's good that you start off with one of my earlier confidence intervals video until you're able to feel comfortable with using that formula. I'm going to gloss over this problem because we want to focus on some new stuff, not this old confidence interval stuff, but it's a good chance just to double check your skills if you've watched my previous videos and want to make sure you're getting it right. So the sample mean is obviously 57.2 grams. Take 1.96 sigma, sigma being 4.2, over square root 60. Less than mu, less than, and x bar, 57.2, and hopefully I'm not going off the screen this time. No, I'm way off. Okay, that's good. Plus 1.96, lots of sigma, and sigma is of course 4.2, over square root of 60. So let's have a look at how we would plug this in on our calculator. Again, feel free to do it algebraically using a calculator, but I'm actually going to show you the TI method for calculating confidence interval really easily, where you don't even need to think about the formula because, like quite a few things, actually does the work for you. That's a great thing about graphic calculator technology. But what we want to do, if you do want to follow it this way, and sorry this looks a little dodgy, but we want to press Stat down here. And you want to go across to tests. And you want to go down to number 7, which is the Z interval test. Okay, so now you should have input, and as you can see there, it's data or stats. Put it on stats, Then you want to type in sigma, and we know that sigma is, of course, 4.2 grams. And we know that x bar is 57.2, as we actually just put up there before. So we got 4.2, 57.2. We know that the number of prawns in our sample is 60. So let's go ahead and calculate. Now, a little extension here, if you want to actually pause the video and do this on your own, it's really good to look at, but look at the concept of confidence interval width and what happens as n approaches positive infinity, and consider what that means, but also consider actually changing the confidence level to 0.99 and 0.98 and see what you get for the intervals as a difference, and maybe write a little report on it. Unfortunately, I could do, a huge series on stats, but I need to cut it off at some point. So just try that independently in your own time as an extension. But again, when we calculate this, we do get a few values here, which I'll write up on the board. So it tells us that the confidence interval is between 56.1, again I'm going to free SF, 56.1 less than or equal to mu, less than or equal to 58.3, where all of these values are grams, because they're the weight of the prawns. And hence, we have actually got a confidence interval where 95% of the time the mean will lie. Okay, so that's great. We've worked out that interval. But the next question claims that she is 95% confident that no more than 10% of the prawns weigh less than 50 grams. Use the confidence interval found in Part A to justify this claim. You may assume that the weights of the prawns are normally distributed. So this is where it gets a little bit more complex, because we're not talking about a population mean anymore. She's claiming that all prawns, not just the average prawns, but all prawns will be greater than 50 grams at most 10% of the time. So, 90% of the time. I'm thinking about the other way around. So that means 10% of prawns will weigh less than 50 grams. So how does she get this claim? And that's an interesting thing to actually work out here. But what we do when we try to calculate something like this is we assume that this lower mean here is, and we take it at the 0.95 confidence interval, so we're 95% sure that the population mean lies within there all of the time. But we take this lower mu value and we treat it as the actual mu value, because that's on the lower end of our sample, and again she's claiming that no more than 10% of prawns will weigh less than 50 grams. So in order to check this out, we set that the mu is greater, it will be equal to 56.1, and because we have the mu is equal to 56.1, and we have the sample standard deviation, what we can do is we can go, well, mu equals 56.1 grams, and we have our standard deviation of the sample as being 4.2, and that's over square root n, of course, because this is for a sample. And we actually use normal CDF to find the proportion under the curve. So in order to find the proportion, we don't actually divide it by square root n here, and that's something I should point out. Although that is the sample standard deviation, it does come in handy when we're actually sampling it. We do use the population standard deviation of 4.2 grams because we're assuming that this is the actual mu. So we're taking the scenario as it is for the population and just saying, okay, we're assuming that this is true, so hence it's no longer a sample, but it's for all prawns because it's the lower end of our expected weight, and we're assuming that that value is true. So in order to do this, we go normal CDF in order to calculate a proportion. Normal CDF, go negative E99. Our upper limit is, of course, the 50 grams that we had before, and our 56.1 is the mean weight, whereas standard deviation is 4.2. So we type that into our calculator, and we go second function distribute, obviously, to get to there first. And when we do type it in with normal CDF, we can do negative e to 99 or negative 1 e to 99, depending on what you prefer to do. And then we go 50, 56.1, and of course 4.2. And we get that the probability that the weight is less than or equal to 50 grams is 0.07319 and you can go to many SF to work it out, but I'm probably going to round it off there. And of course I'll round my final answer to 3SF. But as you can see, the probability there is around about 7.3% if we were to think of it as a percentage. So because it's 7.3%, it is less than 10%, and hence her claim is correct, assuming that that lower bound is the actual population mean, and we're assuming that that is the actual normal distribution. We're assuming this distribution here of, and again, distributions are written in mu sigma squared form, so we're assuming 56.1, 4.2 squared. Okay, and that's pretty much all for doing that kind of test. So if I were to summarize those steps, because I know it was a bit all over the place here where I was talking about how we're no longer assuming that's a sample standard deviation and we're assuming that's a population standard deviation. But again, what you do is you take the lower bound or the upper bound, depending on what the question asks. Is it saying that such and such percentage will be less than or greater than a certain amount? So you take either the upper or the lower bound of that population mean. You treat it as the actual mean, as though it is a real scenario where that is a real mean. And then you take the population standard deviation, you use that with normal CDF, again, to find the proportion, and from that you can conclude whether that claim is correct. In this case it is correct, because of course 7.3% of prawns based on our lower limit on the 95% confidence interval will actually weigh less than 50 grams, which is, you know, 1 in 10 prawns, or less than 1 in 10 prawns technically, but it's still a very small amount, so perhaps a wholesaler will actually get a sale here with the restaurant. So now moving on, and this is the last part of the stats series, actually looking at calculating p-values in order to get 0.99 confidence intervals, 0.80, 0.85, and 0.96 confidence intervals. So I'll go through this, and again, a question worth considering is actually taking some value of n, taking some value of x bar, and actually going through and finding the having a standard deviation set, but actually changing from a 95% confidence interval for mu to a 99% confidence interval for mu, and seeing what happens to the width of the confidence interval. I won't go through that in this video. I think I may have touched upon it in a previous video slightly, but you have a go at it and see what happens there. That's an extension investigation. Again, I would put it in the stat series, but I'm sort of running out of space and running out of time a bit as well. So, here's the actual question. Again, what we'll be doing here is learning how to calculate other confidence intervals. Now, let's start with the classic other than 0.95, which is 0.99, which is being very accurate most of the time. And what we have is we have the general form for a confidence interval. We have x bar, take a, lots of sigma on root n, less than or equal to mu, less than or equal to x bar, plus a sigma on root n. And what the question asks is, if the p percentage confidence interval for mu is given in this general form, then for p equals 95, a equals 1.96. And we know that from the 0.95 confidence interval formula, we know that that is 1.96. Find a if p is if p is 99. So of course that's the 0.99 confidence interval, because the p is the percentage probability. Okay, so now in order to go through this, what we need to do is consider what this value means in context. So let's draw up a normal distribution for this, shall we? So we've got a normal distribution, we've got a mean somewhere in there, we've got a mu plus 2 sigma out there, and we've got another standard deviation in there. Again, it's just a very rough drawing. But 95% of the data lies between the z-scores of, whoops, that's on the wrong side, 95% lies between negative 1.96 standard deviations to the left and 1.96 obviously standard deviations to the right. So this value here of A actually represents the z-score on the upper and the lower. Again, as you can see here, we have take A and plus A. So it's essentially taking into account the z-score for those two values there. That's a really simplified explanation and the one I'll go to just for this video, just for this level of stats. So now what we want to do is we want to find where 99% of the population lies. And of course that means we're going to be expanding outwards, because we need to find where 99% is. And of course we've got to go outwards from 95% to find where 99% is. So this will be greater than negative 1.96, it'll be negative 2 point something. And over here it will be 2 point something or other as well. So again, that value of A that changes depending on the level of the confidence interval is easily calculated just by considering the z-score. That's the main thing to note from what I've just shown you. And that's the only thing that changes, because x bar, sigma, and square root n are of course going to remain the same. It's that value of A that represents the z-score to the left and right of the mean, for which the proportion lies, that will actually affect how wide our confidence interval is. Okay, so let's find the 0.99 confidence interval A value. So in order to do this, we consider the normal distribution, and we go, well, okay, we need to find where 99% of data lies, or where 99% of the time the population mean will lie. And we know that because the bell curve is symmetrical, there'll be a proportion over here, or it's supposed to be symmetrical, not that I've drawn it symmetrically, but we know that there'll be a proportion left or right which will be outside of that 99%, or the 0.99 confidence interval. Because they are symmetrical, we know that the sum of this component and the sum of that component is of course going to make 0.01. So what we do to actually calculate this z value is we consider the idea of finding a quantile, a k value. And I briefly touched up on this a long time ago in the inverse normal video, where I said that the k actually gives you a z-score if we standardize the distribution. So remember, standard normal distribution is where we have mu equal to 0 and sigma equal to 1. And essentially gives us a z-score, which is good for comparison purposes. So now that we have that 0.01 space there and there, we actually think, well, okay, what would it be if we were looking at the proportion below the curve to this point to get that z value? And the answer is not 0.01. That's not our area that we plug into the inverse normal formula. We actually plug in half of that, because we're just looking at the half up to this value here. So the answer is, if we plug this into our calculator, the actual value of A, the z-score, will be will actually be derived from having the area as 0.005, which is half of 1. Again, because the bell curve is symmetrical. And, of course, we standardize the distribution because we want a z-score, which in this case is a value of A in the general form. So now we are able to calculate that value of A, and we're able to get the 0.99 confidence interval value. And I'll show a calculation for the 0.99 confidence interval as well. So, second function distribute, go down to inverse normal and type in the area as being 0.005 and mu and sigma as being 1. And we get the z-score of negative 2.58 when I round it. Negative 2.58, or if you want to be more specific, negative 2.576. So it's up to you as to how many sig figs you choose to go to. I generally like 3, but if you like to go to 4, that's okay as well, considering the original question, the book I got it out of, as an actual 0 there as well, so it goes to 4SF. So this is our value of A, and we treat the magnitude, because of course we consider the magnitude, as what we plug in to the value of A here. So instead of 1.96, the magic number is 2.58 standard deviations. So instead of actually having 1.96 standard deviations to the left and the right of the sample mean for where the population lies, we're actually looking at expanding that to 2.58 or 2.576, 2.58 or 2.576, sorry, to the left or the right. So let's do a 0.99 confidence interval calculation now that we know that this A value is actually equal to, I'll go 2.576 for this, just to be a little bit more precise. So again, we have x bar, take 2.576, lots of sigma on root n, less than or equal to mu, less than or equal to x bar plus 2.576 sigma on root n. And what we do is we think, well, okay, let's have a sigma of 2 and x bar of 22.1 and n as being 6. We can use our calculator to find this confidence interval, and we go to second function distribute, and in fact, sorry, we actually just go into stat, tests, and then z interval, which is the 7th one down there. And when we do that, we type in those values as I've got up on the board there. And because I'm doing it on my calculator, I can quickly show you the difference between 95 confidence interval, 0.95 confidence interval, and the 0.99. But we go to stats again. I'll get my calculator up here and do this dodgy thing. We have as our value of the population standard deviation, we have 2. As the sample mean, we have 22.1. Then for the value of n, we just have 6 instead of 60. And for here, we type the confidence interval as actually being 0.99. Calculate. So at the 0.99 confidence interval, we can round this to be 19.997 less than or equal, oops, sorry, wrong one. Looking at 99% confidence interval, 0.997 less than or equal to mu less than or equal to 24.203. With the 0.95 confidence interval, again we go to the same thing, we go into our tests under stat menu, and we change that confidence interval back to 0.95 as it had before. And we actually get that the population mean 95% of the time lies between there. And I know I've been saying, okay, consider what confidence interval width actually does when you change it. From that you can probably infer it. I won't go into the details, but as you can see, it's quite interesting there, how the value of A actually changes the width. I'm thinking, I don't want to make this go on for too long, so I'll look at an interesting one, probably the most different one. We'll look at a 0.80 confidence interval, a 0.80 confidence interval, and we'll find the value of A for that. So again, I'll show you the method one more time. Hopefully you'll be able to follow along. We've already gone through it, so it should be okie dokie. So, let me draw up a normal distribution, and it will be a standard normal distribution because we want to find that quantile, that Z value, relevant to the 0.80 confidence interval. So, we have mu somewhere in here. And we know that with a 95% confidence interval, I'll always use that as a base. We have negative 1.96. And we have positive 1.96, sorry, and 95% of the time the population mean is in there. I should actually denote this as being x bar in the middle there, sorry, because the population mean will of course vary. Okay, so now when we consider the 80 confidence interval, we're actually saying that instead of having 2.5% down there and 2.5% down there, like with the 95% confidence interval or 0.95 confidence interval, we're actually going to say we're going to have 10% on either side. So we're going to have 10% there and we're going to have 10% there. Obviously not drawn to scale. And so, because we have 10% on either side, again, because it's symmetrical, and it'll be somewhere in this range because it falls there 80% of the time, the population mean, we can actually say, well, okay, if we need the z value, the area under the curve, it's not going to be 20, which is left over, it's actually just going to be 0.10. So we go inverse normal on our calculator to get this value of A, the z value that's relevant to this, again with a standardized distribution because it's a z-score and we need comparison. We go 0.10 as our inverse norm value, and we calculate that z-score, sort of like a z-score I should say, and we can plug that in as being our A value. So I like to go second function distribute down to the inverse normal, and instead of that value we go 0.10, and then we go mu and sigma equals 0 and 1, and we get the value of 1.28. 1.28. I'll just leave it at, and that's negative 1.28, and that's 1.28, and again it means that 1.28 standard deviations that side, the population mean can lie relative to the sample mean, or this time negative 1.28 to that side as well, where it can lie. And again, that's 80% of the time. So our A value is not 1.96 or 2.576. We're actually looking at an A value in this instance of 1.28. So again, we can use this on our calculator. If we were to write out to solve it algebraically, in case you're interested in doing that, we can say that we have a x bar equal to 22.5, we have sigma equal to 2, and we have a n value equal to 103. If we were to write that up, again we're finding a 0.80 confidence interval. We could go x bar, take, and again in this case it would be 1.28 sigma over root n, less than or equal to mu, less than or equal to x bar, plus 1.28, lots of sigma on root n. And again, when we substitute in those values, we get 22.5 take 1.28, lots of sigma, which is 2, on root 103, is less than or equal to mu, is less than or equal to 22.5 plus 1.96, lots of sigma, sigma being 2, on root 103. And again, I'm not going to show you how to plug that in on your calculator because I've done that in previous videos. I'm just going to go to the TI app on here, use that, again, stat, and we go to tests, Z interval, and after we've gone to Z interval, I'm going to assume you know how to put it in now. So we have standard deviation as 2, we have 22.5 as x bar, we have the value of n as 103, and the confidence interval is 80, so it's 0.8, and we've got some values there which I'm about to write up on the board. And as you can see, it's quite narrow considering the standard deviation. So it actually gives us 22.25 less than or equal to mu, less than or equal to 22.75. So again, it's a pretty narrow range, but that's again because it only falls at 80% of the time, and we have a reasonably large n, 103 compared to 6 last time. So have a play around with the n values, the population, standard deviation, and of course the confidence intervals, and try and find some relationships. This was the last video in the stat series. It has been great going through this with you. If you have any questions, comments, please leave them below. I'll be starting binomial distributions very shortly, and that should be a lot of fun. So again, I'll be uploading the first few videos of them this weekend. I've gone through already part of the chapter, but again, I'll be starting them from the beginning with a nice introduction. So thank you very much for listening, and that's all. See you later.